From today, we start part D of Module 1, the last part of Module 1, optimality of algorithms. So in this part, I want to talk about the optimality problem, optimality issue in algorithms. Yeah. D.1, minimum selection problem. In this one, we solve a very simple problem, a typical type selection problem, but it is a special one. Yeah. So let's look at the question first. Our problem number 3 for this class, find the minimum of an array. So that is a pretty simple problem, right? Yeah, everyone can do it. But there is a very important part. You may not think about it. You may never think of it. Optimality. Yeah. So that's a simple example. So we can learn that concept, optimality concept in algorithms. So let us look at a question first. Given an array, A with indices from 0 through n-1, total n elements. Yeah. We need to find index I such that A of I is the minimum of this array. That's simple. Yeah. I believe everyone in this class can find the solution easily. Yeah. But here, the question is not at the solution, if you can find a solution or not. So that's not the main issue. The main issue is if your solution is optimal or not. So think about that. Yeah, the title for this part, optimality. The issue is if your solution is optimal or not. Okay. Yeah. First, we start a new problem type, selection type. I give you 3 basic types of problems in algorithms. Search, sort, selection. Okay? So we did that linear search. Now, selection problem, later, sort. Yeah. All right. First, let me give you the general selection problem. For the general selection problem, it is like this. Find the kth smallest element in a given array. A array with indices from 0 through n-1. Yeah. So for the material in our textbook, you can go to the references, in these 2 sections. Okay? Yeah. And here, our minimum problem is a special case of a general selection problem when k equals 1. The first smallest element. The general, the kth smallest element. Yeah. Here I can give you, so there is a concept we use here representing this k. We call this rank. Rank equals k. Yeah. We use this concept. Yeah. Sometimes we use this concept to describe kth smallest element. Rank k. Okay? Yeah. All right. Next, so let's look at the solution. The solution part is very easy, but let me just go through it quickly. To find a solution, first we do initialization. We initialize our key variable min. So this variable, we use it to store the final solution, the minimum of the whole array. But when we start, we assign the first element in the array to this variable, min. Yeah. Then Later, after each comparison, we try to improve the value of this variable until we get the solution. Yeah, that's the basic idea. Yeah. All right, so let us go through the general steps. Yeah. For the general step, we use it repeatedly. We compare the current value main with the current element A of I. The counter variable I goes through from 0 through n minus 1. Yeah. All right. Yeah. For each comparison, if main greater than A of I, then we replace the current main value by A of I. So we reduce its value. We update it. We improve it. Yeah. Otherwise, we go to the next element and do the comparison with iterations like this. Compare main and A of I plus 1 until we reach the last element when I equals n minus 1. After that, we are pretty sure, so we are very confident that main contains the global minimum value, the minimum value of the whole array. That's what we need. Yeah. So that is the solution. Return main, we get a solution. All right. So that's simple. Yeah. But the next question, to find the solution, how many comparisons do we need? Can you see that? It's pretty simple. Yeah. The answer is n minus 1, not n. Yeah. It is very likely some of you may feel the answer is n, but it's not. The reason is very simple. Yeah. Because for the first element, no comparison. For the first element, it is assignment, right? So when you do assignment, no comparison. Right? Yeah. But after the first element, when you work on each element, you need to make one comparison. So for that reason, you need n minus 1 comparisons. Okay. All right. So that's the solution part. So you can see we've get a solution. Yeah. And we get efficiency, right? So this is efficiency. This is the efficiency, the number of comparisons we need to solve this problem. Efficiency. Yeah. We get it. Yeah. Then after that, then the main question we need to ask for this problem. Is it possible to further improve the algorithm? When we solve a computing problem, we always need to ask this question. Okay? Otherwise, you may not complete the solution. Yeah, if you do not do it, you may not get a, satisfied solution. Yeah. All right. So, but when you ask this question, usually you have two options for your answer. Two options. Yeah. The first option, improve the algorithm. Yeah. It's possible to improve the algorithm. So you should try your best to do it. Improve the algorithm. That's the first option. But there is a second option. You cannot improve it. It is too hard to improve it, or there is no way to improve it. Okay? Yeah. But anyway, but you cannot improve it. Yeah. in that situation, you may need to do one thing, one important thing. So that is convince people that it is already optimal. The solution is already optimal. Okay, so nobody can improve it. So don't waste your time and money to improve this algorithm, because you cannot. But for the second option, it is not easy. So you can see it is not easy. Why? How do you convince people, right? How do you make strong argument to convince people it is optimal? So that is what we need to do in this video. We need to do it. For this particular question, first, we need to determine if it is optimal, right? We need to get a conclusion first. After we get conclusion, we feel it is optimal, then we need to make convincing arguments. Really strong convincing arguments to make people feel comfortable that this algorithm is already optimal. So let us do this part. Okay. So our next question, that is the harder part. Convince people. When we try to convince people, what do we need to do? So here we need to work on this tough part. Among all the possible algorithms solving this minimum selection problem, for all the possible algorithms solving this problem, how to show that this one is optimal. Our current solution, so this solution is optimal. That's what we need to do. So you can see, not that easy, right? At this point, based on your knowledge, it is not that easy, right? So let me point out another tough part. So that make this problem not that easy. Okay, So what's that part? Among all the possible algorithms. So look at this requirement. Among all the possible algorithms. All the possible. Okay? So when you try to look at all the possible algorithms, how can you do that? Right? How can you study all the possible algorithms, right? So that is hard. Okay? So here, think about those algorithms, including unknown algorithms, right? All the possible. Some algorithms unknown. Those algorithms have not been developed by people at this point, unknown. Because in the future, many other people, they can develop new algorithms solving this particular problem. So unknown problems, right? But when you try to convince people, you should include those unknown algorithms, right? Not just the known algorithms, all possible algorithms, including known and unknown at this point, right? So that's the reason it is hard. Okay. Sometimes you may even wonder, is it possible? Is it possible to study those unknown algorithms? By your intuition, it looks impossible, right? by intuition. How can that be done? Right? Yeah, so you will see we can do it. Yeah. So from our next slide, we can do it. We find a way to solve this problem. There is a smart way we can use to solve this problem. Yeah. So let us look at the solution. Yeah. All right, so now, how do we convince people that our algorithm is optimal? Yeah, so let's work on this part in this slide. Yeah. All right, here we need some imagination. Yeah, so very smart view. Yeah, right view based on our real world experience. Yeah, in order to convince people. Yeah, so we use some common real world experience. You know, your audience, they have the similar experience. Yeah, so they can understand your point easily. Yeah. So what kind of experience? Yeah. So when we do comparison, we do analogy in the sports game. Yeah. In a sports game, people play matches, right? Tennis game, think about the tennis game. Two players, they need to play several matches, right? Yeah, we can use that analogy to understand our convincing argument. Yeah. All right, yeah. So we consider one match between two players. We treat it as one comparison. The stronger player will be the winner. Yeah. So the number with smaller value we treat as the winner. The number with smaller value, not larger value. Why? Because our goal is find the minimum value, right? Minimum value, the smaller one will be the winner. Yeah. So for that reason, when we compare two numbers, the winner is the one with smaller value, less than. Yeah. If A less than B, A is the winner. Okay, all right. Equal, then we get tie. Okay, yeah. Greater than, A greater than B, yeah, we get a lose. Yeah. Result. It lose for that match, that particular match. Yeah. All right. So with this kind of connection or background experience, now we are ready. We can run our convincing argument. Yeah. So let me start a sequence of arguments. Yeah. One by one. Yeah. Each one very easy to understand. After we go through this whole sequence of statements, our audience should get convinced that our solution is optimal. Okay? All right, so let me start with the first argument. Imagine that Ming is the final winner. Yeah. So at the end, the variable Ming returns a value, so that value is the final winner. Okay? So that kind of equivalence can be seen easily, right? Yeah. Now let us use this argument for the whole story. Yeah. All right. This winner, it needs to beat all the other elements in the array through comparisons, directly or indirectly. Yeah. Why people call this one the winner, right? You're supposed to beat all the other players, right? Otherwise, how can people agree that this one is the winner? Yeah. So the second statement tells us general result. a general fact, right? Yeah. But here, the special phrase, directly or indirectly. Directly, B directly, that's easy, right? We compare A and B, A less than B, so A beats B directly. But what do you mean indirectly? Here, let me give you an example. A beats B indirectly without a comparison between A and B. That's the meaning. We do not do comparison between A and B, but we know A beats B indirectly. That's what I mean. Okay? All right, so let me give you a simple example. Suppose A less than C and C less than B. Can we get A less than B? Do we need a comparison between A and B? We don't need, right? Yeah, because by the transitivity property in inequalities, here, when we work on these inequalities, by the transitivity property of the basic inequalities, we can get A less than B. That means A beats B indirectly. So mathematically, we have this transitivity property when we do inequalities. Yeah. But here it is slightly different in our real world experience. Yeah. Because in the real world, A player beats C player and a C player beats B player. It is not necessary that A player beats B player, right? Yeah. In the real world situation, we may not really get this transitivity property. It may not be true. Yeah. It may not be true. Yeah. It could be A beats C, C beats B, and B beats A. It could happen. Yeah. All right. But here, we do not really get to that part. Yeah. So we don't want to, go to that special situation. That could happen, we know. Yeah. But here, because in our comparisons, we won't have that kind of situation. So we can eliminate that case. Yeah. All right. So let us continue our convincing arguments. Yeah. All right. If an element loses once, it is eliminated. Yeah. If one element loses to another element, then this element cannot be the winner, final winner, right? Yeah. It cannot be the minimum. Yeah. So this is also true. So no winner can lose even once. Yeah. So that's a simple fact. Yeah. The next one, each comparison can only eliminate one element. Each comparison can only eliminate one element. Is that true or false? Yeah. So try to understand. One comparison. Okay. Yeah. One less than. Yeah. Here. Yeah. Here. Yeah. When we talk about this one. Yeah. Here. Yeah. We may like to eliminate the tie case. If it's tie, then they need to play extra game. Okay? Tiebreaker. Yeah, they need to play that. Just the one player has to beat another player. Yeah. Yeah. So let's assume that. Yeah. But in that situation, yeah, each comparison, only one player gets eliminated. We cannot eliminate both, right? After one match, both players eliminated. That cannot happen. Yeah. Another case, nobody gets eliminated. That cannot happen, right? Because one winner, one loser, so the loser get eliminated. Yeah. All right, so yeah, the next argument, we need to eliminate n minus 1 elements. Yeah, because all the elements except the winner must be eliminated. So we need to eliminate n minus 1 elements. So thus, we need at least n minus 1 comparisons. Yeah, because one comparison, you can only eliminate one, but now we need to eliminate n minus 1, then you have to do at least n minus 1 comparisons, right? Yeah. So now the last argument, the last one, okay? Yeah. After we go all the way here, we get our last statement. Now we have a solution with exact n minus 1 comparisons. We have it. Okay? Yeah. We have it. That means our solution is optimal. Yeah. We have it. We achieve it. We achieve the best result that people can make. Yeah. n minus 1 comparisons. We make it. Yeah. And then nobody can use fewer than n minus 1 comparisons to solve this problem based on our analysis. Yeah. That means our solution is optimal. Okay. All right. Yeah. So now the final conclusion. Yeah. So for all the whole story, yeah, I want to make the final conclusion. Yeah. In this solution, in this solution, we use a very simple method, but it's a very important method. Yeah. Elimination method. Yeah. Every time winner, loser, the loser gets eliminated. Elimination method. So that is the elimination method. Okay? Yeah. Try to eliminate as many as possible elements. So that is the elimination method. Yeah. Here you can see it looks simple, right? Yes. I agree. The idea here, very simple, but later you will see this method is very useful. It can help us solve many problems. Some of the problems pretty hard. We can use this elimination method to solve it. Here, I can use this video as our introduction to this elimination method. All right, so let me finish my first video, D.1, right here.